Hey guys, I guess you're space fans today at Live Science. I'm your host, Judy Stroh. With me, as always, it is Mindy Weisberger. How are you doing today, Mindy?
As always, I'm great, Judy. How are you doing?
I'm glad you're always great. That actually does make me feel better. So today we're talking about the James Webb Space Telescope.
Yes. This week was the most recent big milestone that the telescope reached on Monday. It parked in what is going to be its new address, which is about 1 million miles from Earth. So since its launch on December 25th, this has been like just such a long time coming. I mean, it's the project. The project started more than 2 decades ago. The telescope it's often referred to as NASA James Webb Space Telescope, but it's actually a collaboration between NASA, the European Space Agency, and the Canadian Space Agency. And cost about $10 billion. It was the size of a school bus. It weighs 14,000 pounds. And it is now parked at the second Lagrange point, or L2, 1 million miles from Earth.
I mean, I don't really cover space stuff a lot. So whenever I get to learn about this stuff, it's like, wait, what are we doing now? We're looking out at the universe. We're going to learn about the formation of the universe. I still don't really understand quite how we're going to do this, but that's why, we bring the experts on, right?
Yes. So Webb is the most powerful space telescope that's ever been launched. And what it's going to do is it's got an array of instruments, but what I think people are most excited about is its infrared capabilities. So it's going to use those. Because it's got such powerful optics, because its mirror is so large, it's going to be able to see very, very faint, very cool objects. It's going to be able to peer through dust. So it is perfect for looking for very, very old objects. So it is literally going to be looking back through time to just after the Big Bang, to when the universe first formed, which is super exciting.
I guess we're happy that space is so dusty that it gives us a lot of information to work with. Yeah.
Well, the dust is often what hides the stuff, but the dust is also where where the magic happens in space. So
a lot of information in that dust too, I'd imagine.
Oh, absolutely. So yes, there a lot going on. It took a lot for the telescope to get to the point where it's at now, and there are of course very specific reasons why it is where it is at this very specific spot that is 1 million miles from Earth. And so to find out about how it got there, why it's there, I spoke to Dr. Stephanie Marilyn, who's a deputy project scientist for planetary science for the Webb Telescope and a planetary scientist at NASA's Goddard Space Flight Center.
Wow, so she's working on it itself, yeah?
Oh, yes, very much so.
That's exciting. I'm looking forward to it. Okay.
Congratulations on this monumental achievement. I know that a lot of our readers at Live Science have been following along with Webb since it launched on December 25th and have been closely watching every deployment milestone along the way. So now with the mirror unfolded, the sunshield deployed, and Webb orbiting L2, do you and the Webb team feel like at least some of the tension can be released at this point?
Oh my goodness, yes. It is. It's been a huge sigh of relief to see how beautifully everything's been executed on this mission so far. It's been fun to hear our management and project team talk about, oh, we made it look so easy, but that's just, all the blood, sweat, and tears that went into the years of making sure it did look easy. But yes, it's been a huge sigh of relief, and we're really looking forward to the next steps.
So tell us about your role as deputy project scientist for the Webb Telescope. Could you please explain what that entails?
Sure. So my job on this project is to make sure that we have this giant, extremely sensitive, massive space telescope designed to look at the first stars and galaxies across the universe. And I am to ensure that we have the capability to look at the brightest objects in the sky that are flying by the rest of the universe. So objects in our own solar system. And this includes basically everything that we can fit in our field of regard, which is we can't point the telescope towards the sun or the earth because we have a sun shield. So that kind of gives us a limited field of view for the solar system of Mars on outward. But we can do things like near Earth asteroids and comets as they come into the inner solar system. And so those are also part of our science plan. But these objects actually move really fast. And so we have a big floppy sensitive telescope, and we have to be able to move it across the sky at a rate, a speed limit that matches something like an asteroid or a comet. And so that was one of my main tasks. And also we have really bright objects like Jupiter and Saturn and Mars, especially at infrared wavelengths. And so making sure we had capability to do observations and science that's compelling for these kinds of objects.
And now Webb is going to be looking at all these objects from its new address, which is about 1 million miles from Earth. So about L2, which Webb reached earlier this week on Monday. Why was this particular position selected for Webb's orbit? It's obviously much farther away than Hubble, which of course will prevent repair missions. So why so far away, and why this particular spot, L2?
There's so many advantages for L2, especially for an infrared telescope. So because we're not an optical telescope the way Hubble is, we're very sensitive to thermal radiation, otherwise known as heat. And unfortunately, the Earth, or fortunately, I guess for us, the Earth is warm. And so any radiation the Earth or the moon actually is emitting is something that we're very sensitive to. So being as far away, we're kind of in a nice cold, dark region of space where we don't have to worry about the thermal effects of the Earth and the moon. It's a nice stable point, though, that we can actually orbit the sun with the Earth. So we are always in direct communication and access to the Earth, and we're in an orbit at L2, so we are in the shadow of the Earth and the moon either, and so we have direct access to the sun as well for power.
Well, speaking of the sun, as far as Webb's science mission is concerned, as much as the sun is there, but those instruments are going to need to perform under conditions of extreme cold. So, how is Webb going to manage to do that?
So we have a funny looking shaped telescope for a space telescope. It almost looks like a sailboat. And the reason for that is because we have an extremely large mirror to make it a sensitive telescope to look at the first galaxies of the universe. And so having such a large telescope itself, we have to be able to protect it for the radiation of the sun and the heat of the sun. And also, we don't have a tube that we could have actually fit into the fairing of a launch vehicle that could actually deploy in a way that would have been far less technically complex than what we already have. So having a deployable telescope, so mirrors that had to actually unfold, having a sun shield that was sort of a shield as opposed to a tube was much easier to engineer, design, and implement. And so that's one of the advantages. We have to get SPF of about 1 million for the cold side of the telescope to the warm side of the telescope. So the hot side's almost 190 degrees Fahrenheit on the hot side, and minus 400 degrees or almost 400 degrees Fahrenheit on the cold side. So it's extremely hot, almost boiling water, to extremely cold, say frozen liquid nitrogen on the cold side. And so being able to do that, we had to have a large sun shield that was deployable because it had to be large enough to protect our telescope and the instruments itself.
So looking at where Webb is now, there's still a few months of fine tuning the mirror ahead, tweaking the alignment, other tests before Webb officially opens its eyes and looks at the universe. So what are some of the observations that you're looking forward to the most?
Oh goodness, I'm so excited about so many programs. Obviously, my own are going to be the greatest. So I'm a comet astronomer, and so I'm involved with leading a number of programs on comets in our solar system. We just think they're like the fossils of how the planets and our solar system actually formed, and so understanding that is really interesting and compelling for a lot of people in both planetary science and astrophysics. But some of the more exciting things that I'm excited about are things like studying ocean worlds in our solar system. So we're looking at like the moons of Europa and the moon Enceladus around Jupiter and Saturn. And these particular moons we think have giant oceans underneath their icy surface, and we think those oceans could actually enable biology and maybe have some really interesting chemistry. And so what we do is we study whenever they have these sort of geysers that come out of the surface through the cracks, and we can actually look at those geysers with JWST and study the chemistry of these oceans and see if they're like ours, or maybe they're different, maybe they're like Titan. So we'll see what kind of crazy chemistry they have. And comparatively, we'll be looking at planets in other planetary systems, so planets around other stars, and seeing whether any of those are like the ones in our own solar system. They have atmospheres like Earth, Venus, Jupiter, if they have liquid water, if they have crazy dust storms like Mars. And these are all the really cool things that we're going to be learning about planets in general in our solar system and in other planetary systems.
You mentioned comets. So what are some of the ways that Webb is going to give scientists and researchers like yourself a new perspective on comets, that or ways to see them that you haven't had before?
So with the sensitivity of Webb, we can actually see comets in very distant places in their orbit, so much further out than what we can observe with ground-based telescopes, for example. And that's just because it's more sensitive. We don't have to worry about the Earth's atmosphere actually, inhibiting some of that signal, and having a large space-based telescope, we get a lot more sensitivity. So we're going to be looking at comets in the outer solar system as they come in, which is a very unique study that we haven't really been able to do for very many objects, just because they are so faint. They're not active necessarily in the outer solar system. And so this is something that's going to, give us some new insight into how comets start becoming active in these fuzzy objects in the sky, which turn into these beautiful streaks across the sky. We also have access to them during Earth's daytime. So we have 24/7 operations with JWST. So we don't have to worry about when the sun goes down to actually conduct our observations. So that gives us access to a lot more objects, because comets are moving across the sky, as all objects in our solar system. So we don't have to worry about whether or not they're in the sky during daylight or nighttime, wherever our telescope may be. So that gives us a lot more access as well. And finally, we have access to studying chemistry that's in our own Earth's atmospheres in these objects. So our Earth atmosphere actually blocks out signals from certain molecules, because they are actually molecules that reside in our atmosphere. And so we can't study them in other objects from the ground. So having access to studying those kinds of things is something we only get from space.
Well, clearly there is still so much to look forward to, and I personally can't wait until the first images start coming back and we start seeing things the way Webb does.
Absolutely. I can't wait. And I know there's going to be so many new discoveries that we haven't even thought of yet. Well,
Dr. Marilyn, it has been such a pleasure talking to you. Thank you so much for being here today.
Thank you so much for having me.
There she is.
There's the live me, anyway.
Wow, Mindy, that was some thick science there. Like, you actually got to talk to someone on the ground floor. That's exciting.
That was it was really exciting to get her perspective on how the telescope got to where it is and what it's going to do next.
I mean, to say that they don't even know what they might find is kind of like tinglies. That, like, I love when NASA gets excited by these things, because, like, what could we actually see out there?
Sure. Well, this is one of the variables of doing any observations in space, is that there's the possibility that you're obviously aiming your telescopes at places where you think it's likely that you're going to find something that you are expecting to look at, but there's the possibility that you may see something that you weren't expecting, or that what you do see is going to open up just a whole new array of questions that are going to lead to new discoveries. And with a telescope as powerful as Webb, that is a very, very real possibility. So yeah, that's one of the things that's so exciting about this.
Such as space exploration, so many more questions to be answered. But, like, so when exactly are we supposed to be getting this information back, these images or whatever?
Well, so even though the mirror has all of the segments have unfolded and the sun shield has been deployed, but there's still some small adjustments that are going to be made in the alignment. So this big, the big iconic gold mirror that we saw in some of the animations that you were showing, that is just this massive thing that is I think about 21 feet in diameter. And it's made up of all these segments, and so basically, to fit the telescope into the nose of the rocket when it launched, it basically this all had to be folded up. So everything was all kind of squinched up, and then the segments were opened and they were aligned, and the big alignments have been done, but there are still some very, very small alignments that have to be done. Like we're talking about something that's of a magnitude of smaller than the width of a human hair, just to. So we're looking at about 5 months approximately of making those alignments and then taking test images, aligning with each of those individual segments, aligning the images, stacking the images, and then being able to getting to the point where essentially you've got this one big segment that's like one giant eye that's going to be taking one image, one uniform image.
Goodness. Okay. Yeah. 5 months. I'll set my clock. We'll do another live then, but only then. No, I'm sure we'll be talking about this for so many more months.
Right. Well, of course, the people that are looking forward to it even more than we are the scientists that are in line for the first observations. And this is I spoke to one of those scientists. So Dr. Jackie Faraday, who is she's an astrophysicist, a senior scientist, and a senior education manager at the American Museum of Natural History in New York City. So she and her team are among the some of the first scientists that are going to be looking at observations from the Webb Telescope. And so and she spoke to me about it.
All right, let's take a look.
Dr. Faraday, thank you so much for joining us.
I'm happy to be here.
So you were one of the first scientists who's part of Cycle 1, the telescope's first round of observations. So what exactly are you going to be looking for?
Yeah, so about a year and 4 or 5 months ago, there was a call for scientists to put their best ideas in of what shall we point this telescope at, this shiny, beautiful new window onto the universe instrument. What should we point at? And so a lot of astronomers got together with their best ideas, and then a peer-reviewed group came together and voted to see what science should be prioritized. And the one that I led that I am very excited about is there are a collection of objects that are very cold, that are near the sun, that really push the boundary on the word planet, but they're isolated. So they're what we call brown dwarfs. So they're the coldest compact sources that can form the same way that stars form. And the ones that I put into study with the James Webb Space Telescope are the ones that are the coldest that we know. And amongst that class, I chose a selection of them that looked like they were extremophiles, meaning for what we know about them right now, we've been just like begging for photons from them, from the telescopes that we have had access to. I found diversity, like a lot of diversity in them. And I selected the extremes in the diversity, the ones that were the very brightest and the very faintest for the same temperature. And that indicates that clouds and atmosphere dynamic, maybe like something different in their chemistry, drive them to look different. And these are critical objects because they're basically like studying Jupiter, but it formed outside of our solar system. So it's extremely relevant to interests in exoplanetary atmospheres. And so I have 12 objects that are in my target list, and my teams. I shouldn't say I have a whole team of people that I'm working with. And James Webb is going to look at them, and we're going to take spectra. We're going to put the light through the spectrographs that are on James Webb, and we're going to break that light up, and we're going to look under the hood on those atmospheres and see what's going on.
So you know what? The last time that we spoke about the Webb Telescope, you mentioned that a key principle for understanding the early universe, and the formation of stars and planets is follow the dust. So how does that apply to what you're going to be doing, and how is Webb going to help with that?
Yeah, so dust comes in a lot of different scales. There's large scale dust, dust that dominates galaxies. There's dust that dominates star forming regions. There's dust that dominates like remnants of dead stars. And then there's dust in the atmospheres of planets, of brown dwarfs. Brown dwarfs have, and when I say dust, it's like condensates. You can think of them as like particle stuff. Clouds come in different forms. We have beautiful water vapory, nice clouds here on Earth, and there may very well be water ice clouds on some of these objects, but then they probably also have a mix of other kinds of clouds. There's enstatite, there's fosterite, there's things that you might be more familiar with, corundum, which if you add the right impurities to, you get, which is like a dusty material, you get sapphires and rubies and gems, like rare gems come in these forms, and we find them in the atmospheres of these objects. And so we can study that and the effect of that if we have something like the James Webb Space Telescope, because they have strong signatures in the near and mid-infrared.
Okay, and when it comes to brown dwarfs specifically, how will Webb help you find and study them in ways that have been challenging for other telescopes up till now?
So the deal with these objects is, like I was alluding to before, they are at the limit of what our current technology can do. And they were discovered, the majority of the ones that I have that are on my program, they were discovered with the Spitzer Space Telescope. Now, everybody talks about how Hubble was a precursor to James Webb, or how they're like a family of telescopes, but really the true precursor to James Webb was the Spitzer Space Telescope, because it covered the same wavelength. The James Webb Space Telescope looks in the infrared. That's what your eye can't see. And the key to studying these brown dwarfs is they don't give you much of any light at any other wavelength besides infrared. And so you need a telescope like James Webb. And so we have infrared detectors on Earth, on detectors on big telescopes, but they don't go deep enough. They can't actually extract the information I need. We beg for the photons from them. And Spitzer was a beast at discovering these objects. It was so important, but it also wasn't able to do what James Webb is able to do. It's got a really beautiful spectrograph. It's a much larger telescope, so that we can get those photons. We can get rich amounts of photons from these objects that are essentially invisible at other wavelengths, and study them with the detailed instruments that are on James Webb. So that's why we need James Webb to do this. And James Webb makes it easy. Brown dwarfs are really popular targets for the James Webb Space Telescope, because they're high reward. There's a lot that you can get uncovered right away, and they're relatively bright and easy for James Webb to do.
Right. Well, what are some of the other things that people are going to be using Webb to look for?
Yeah, so it's a total range. It's a total range in what people are going to do. Some of my favorites are young stellar objects. So young objects are very dusty. They're enshrouded in their natal environment because they've just formed out of a big molecular cloud, and there's gas and there's dust surrounding them, and there's a lot of action happening. There's a lot of like, what do you call these things that kids throw? Tantrums. Young stars throw a lot of tantrums. And as they do, they like eject material and that goes shooting out. And it's really, really beautiful imagery, but it's also dangerous and it's violent. We want to understand the processes. And so there's things called Herbig-Haro objects that are very young stars that are shooting out with disks, with jets that come out of them, that are pulsing through like shock waves of dust that slam into the energy that's coming from a young star that's throwing a tantrum. And we're going to be able to understand better the processes by which young stars end up evolving and, starting to form their planets and moving on that way. There's also the dust around dead stars. There are people that are looking at the shells around recent supernova remnants, or older supernova remnants, or newly formed novae that just went off. Stars die and they just eject a bunch of material, throwing out huge clouds of gas and dust that again move through shock waves. Lots of interesting dynamics of material and astrophysics go out. And then there's the stuff that's at the farthest extent, which is the first galaxies, first stars. And you want to be able to see what the dust was doing back then, and you want to have access to the redshift, to the galaxies that are redshifted so far into the red, they're out of the optical, they're out of where Hubble would see them, and they're in the infrared. That's how you're going to find them. So you're going to get clues as to what was happening when the universe was in its baby state. So we're going to get baby pictures of the universe.
Yeah, so there
runs the gamut. Everything.
Yeah, no, there's so many exciting things to look forward to, and I can't wait for them. But to get to this point, there are so many moving parts that are part of Webb. Like and everything had to come together perfectly to get to the point where we are now. So, but all along the way, one of the pleasant surprises that's come out of all this is that Webb is likely going to be able to keep going a lot longer than was originally calculated. So it was originally going to be a 10-year mission, and now, because the fuel use was so efficient, it looks like there may be enough to keep it going for possibly 20 years. So what are the possible implications of that for science, and how might that impact your own research, having Webb online for a decade longer than they initially thought it would be?
Well, my own reflection on that is that it takes the pressure off a little bit. There was a lot of pressure if we were only going to have this telescope for the shorter amount of time, that you really, really had to make sure that the science you put out right away wasn't necessarily that risky, because you didn't want to waste telescope time. And it also allows us to keep trying at a different project and grow with a project, because every single data point that we get from James Webb is probably going to open up about a bucket load of new questions that you're going to want to say, okay, we got to go back. I need more data from there, which is what always happens in astronomy, that you start with a project idea, you have a question, you formulate it, you have a hypothesis as to how you can get an answer. You have data that you need to acquire to do that. You get that data helps you understand how to move the answer to that question in a direction that's getting you into real answers about the universe. But then it almost ultimately leads you down a road where you're like, well, what about this? And what about this? And what about this? And now it means that we'll have more time to follow up on what will probably be intriguing new directions that we get taken. It'll also mean we have a longer baseline on our data. So you're able to do longer stream things. There's a lot of things in astronomy that you want to look at over a long amount of time in order to see how they're changing. Taking a snapshot of the universe at a given second tells you one thing that's going on, but it doesn't necessarily tell you everything. We have a dynamic universe that we live in. And so like I study weather patterns on brown dwarfs. I'd like to revisit objects a couple of times. And it's nice to know that we're going to have longer to be able to do this with this amazing telescope.
Well, it's going to be really exciting to see all of the things that are coming out of these observations. And yeah, I cannot wait for that.
Yeah.
So Dr. Faraday, thank you. Thank you so much for being here. It has been a pleasure talking to you.
I always love talking to you, Mindy.
Mindy. Goodness. So that's really cool about the fuel.
Yeah, no. Apparently, that was something that I think scientists on the inside knew about this a while ago. It was news to me. I first heard about it at a NASA press briefing on Monday after the L2 orbit insertion. They said, "Yep, looks like we're going to be good for 20 years." And so yeah, it's going to be there, going to be operating. Well, it's interesting because the telescope that's kind of the companion telescope to looking at the universe, Hubble, that is still in operation after, it launched in the 90s. So
all right, so set my clock for 20 years. We'll do another live stream.
Yeah. Well, of course, Hubble is much closer to Earth. So Hubble, there have been there have been service missions to Hubble to actually do repairs. And that is not, at least for now, that's not possible. In 20 years, who knows? But for now, that's not possible with Webb because it's a million miles away. It's just
million miles, schmillion miles.
What's a million miles?
cut to 3 months from now, we'll totally be more efficient fuel on that as well.
Sure.
Um,
But yeah, it is it is going to in 5 months when we start seeing the first observations. It's going to be a whole new view of the universe. And in fact, when Webb launched on December 25th, Stefan Israel, who's the CEO of Arianespace, which is that's the company that built the rocket that carried Webb into space, he said that on the launch stream that NASA was running, that after Webb, we will never see the skies in the same way again.
mm, mm.
So,
I mean, there's a lot of stuff out there that honestly, we haven't looked at the skies in the same way since NASA. And that was 50 years ago.
it's interesting listening to what Dr. Faraday is talking about in terms of just, when she's talking about stars, their births and their deaths, and they're so dynamic, and that's something that's really hard to get a sense of from here. Even if, and most of, like many of us who live in cities where there's a lot of light pollution, it's really hard to get a sense of the night sky and just the quantities of stars that are out there at all.
Yeah.
Let alone, but even if you're out in a desert, even if you're someplace where light pollution is low and you can see, a much clearer view of the night sky, the stars are really small and far away. There, you can't get a sense from here of just how much is going on and how much is happening. And not, obviously a lot of it happened in the very, very distant past. But yeah, it's going to be really something to see some of the image evidence coming back that is going to point to how stars form, how they die, how galaxies form, how planets form. Yeah, there's going to be a lot to look forward to.
Yeah, I just wanted to feature a comment from our YouTube audience. And William says it'll be wonder what the telescope will show us. And I couldn't agree more, especially after all this explanation for my plebeian self of space material. But yeah, like I have to go camping upstate to be able to like see any stars. And I know I did 2 years ago with Hanukkah, and we were just like staring, and I'm like, what? That's Jupiter right there? It's like,
yeah,
pretty mind-blowing stuff for
sometimes, I mean, sometimes even over, like, I'm in New Jersey, right outside of New York City, so a lot of light pollution. But there's some nights where you can see Venus, you can see Jupiter, sometimes you can even see Mars. So even in light polluted areas, and there are certain there are some constellations that are frequently more visible than others. So it is still possible to do some backyard stargazing, even in some place that's fairly close to a city. But yeah, I know that a lot of our I'm hoping that a lot of live science readers are looking forward to this as much as we are, and they can get updates. I know it's going to be 5 months until we actually start getting the observations back, but you can get updates on what's happening at Webb at livescience.com and at our sister site space.com, of course. And we have articles that you can check out on everything from the construction of the telescope to the launch to what it will see when it opens its eyes, and we will be there every step of the way. Can't wait.
Wonderful. Thanks again, Mindy. Till next time.